All right, I'm going to be talking about the same things. Okay. All right, thanks. I'd like to thank the organisers for putting on the workshop. As you will notice, I'm in the School of Electrical Engineering, Electronics and Computer Science, or EECS, as they're called. For my sins, I'm the head of Electrical Engineering and Electronics. Although my background is in quantum physics, I sort of come at quantum filtering partly from an engineering point of view. What I'm interested in is actually practical quantum filtering. So using a measurement record, a continuous weak measurement record, to do incoherent feedback on a quantum system using state estimation. That's what I would like to talk about, or some of the things I've done over the last few years. Because I'm head of department, unfortunately I haven't had any time to do much new work on this, so I'm going to talk about some work that I've done over the last few years with some other colleagues. So apologies if you've seen some or all of this before. Right. The unhappy face there is because I always hate using outline slides. Outline slides always seem to be the same for everybody who does them, so I try to avoid using them. But today what I'm going to do is I'm going to talk about two different things. So I kind of needed to tell you exactly where I was going. What I'd like to talk about is something that came up last week, which is parameter estimation. That's some work I did with Kurt Jacobs and Charles Hill a few years ago, and then talk about approximations of the stochastic master equation itself. Okay? And then at the end, what I'll do is I'll try and sort of point out a few things that I think are interesting and I think that need to be answered. Okay? Right. So why efficient quantum filtering? Very simply, quantum filtering as it's currently done is very computationally intensive. Okay? It's very, very difficult to create the stochastic master equations for state estimation and solve them in time that's quick enough to actually do something realistic with them. So we need to make approximations. So that's where I'm coming from. Right. My personal prejudices about quantum filtering come from my background in classical state estimation and classical tracking systems. Okay? The way that it's normally presented is you have a conditional evolution operator or a conditional density matrix increment like this. There's a Hamiltonian term, there's drift term, diffusion terms, and so on. Hopefully everybody is fairly familiar with this. And then at the end, when this is presented, this is the evolution of your density matrix. At the end of that, then there's always a throwaway comment, well, the measurement record looks like this. Okay. Now, from my point of view as an engineer, okay, although I have no formal qualifications in engineering, I'm a physicist, as an engineer, the measurement record is the only thing that we have access to. Okay, it was brought up in Pierre Rochon's talk last week, the inaccessibility of the actual underlying system in a quantum system. What Pierre called the true state, I would call the state estimate, if you like. I'll come on to why that is in a minute. But basically, in a classical system, we have a system, a physical lump of material, and we can interrogate that without destroying any information. The difference with a quantum system is all we have about that is the single measurement record that we have, and the act of measurement affects the evolution of that system. Okay? So this is the way I look at things. Okay? The first thing we should do is take the measurement. Okay? There's the state. Okay, so the current estimate of the current state of the system, it represents effectively all of the knowledge that we've extracted from the system. It's our best guess about what the system is doing. The only thing we know about the system is what we have learnt from that measurement record or some prior experiment to characterize the Hamiltonian or so on. So what we have is we have this measurement record dy. We can calculate from the measurement record dy, we can calculate the innovation. The innovation is the difference between the measurement record and this thing here, which is the expected measurement. This is what we should measure if our state is correct. Okay? If, in the case of a classical system, if there's no difference between what we measure and what we expect to measure, we've learnt nothing from that measurement. All that's happened is that the measurement has just confirmed what we already knew. Okay? John sort of pointed this out very eloquently last week. So it's only this innovation that really tells us anything new about the system. Okay? So this is where the innovation comes in. The innovation is then used to update the conditional density matrix in this form. Okay, so this is the DW here. It has a very similar form to classical filtering. Okay? In the classical engineering filtering world, this is very explicit. Okay? This is the difference between the thing that we measure, the thing that we actually measure, and the thing that we expect to measure. Okay? That's the new information that we've learned. Obviously, with a quantum system, the act of measurement affects the system and sort of introduces noise and so on. Not necessarily true in a classical system. Okay? Right. So, as a theorist, particularly a numerical theorist, what I'm interested in is extracting information from this measurement record as best I can. In my case, I'm interested in extracting information as best I can using approximations which simplify those calculations. They make it easier to calculate and then easier to feed back that incoherent signal. In my case, I don't have a measurement record. I don't have an experimental measurement record. So the obvious thing for me to do is to use an SME, stochastic master equation, to generate, initialized in a pure state, although it doesn't have to be, and that SME, the only role it plays is to generate a measurement record. Okay? So all it's doing is it's got a little black box with a stochastic master equation in it, and all it's doing is pumping out a measurement record. And the only information that I learn about the system is from that measurement record, which means that I need a second stochastic master equation, where the second stochastic master equation is interpreting that measurement record as if it was an experimental record. I can take away my first SME, and I can plug in an experiment, someone will give me access to one, and then I can do the state estimation. Okay? Now, in most cases, we'll assume that the SME2 has an accurate estimate of the system Hamiltonian. Okay? We know what the system evolution is. In fact, the first half of the talk won't be that case. We're actually going to estimate the Hamiltonian as well. And we know the measurement strength. Okay? The measurement strength, the strength of the coupling between my measurement device and my quantum system. And I'll come back to that right at the end. We'll assume that it's initialized in a completely mixed or completely unknown state. So I don't know what it's doing to start with, and the only information I have is the information that I collect from that measurement record. SME2 is run with small time steps and a non-ideal measurement record. So I can't, the measurement record isn't perfect. Okay? There's potentially other sources of noise, there's bandwidth limitations and so on to that measurement record. But that's the only thing that I have. Okay? The only other thing, so the only thing I use the measurement, the SME1 for is the measurement record. I also use it as a ground truth. Okay? In classical filtering, you call the ground truth something which is I know for certain. Okay? SME1 is the only way that I can characterize how good my algorithm is, how good my filter is. So I'll calculate the fidelity or the trace distance, in this case the infidelity, 1 minus the fidelity, between the estimated state and the real state. Okay? So I use it as what's called a ground truth in classical filtering. Right. This came up very briefly when Pierre was talking last week. The integration scheme that you use is quite critical to the performance of your filter, in the sense that many filters or many implementations of filters can be unstable if the correct numerical integration scheme isn't used. Typically, I would use the Milstein correction term, and I'm currently testing out Pierre's modified version, which actually seems to be much more stable. So I'm quite pleased that at least one thing I've learned from this workshop is a different way of doing it. But you can also use a thing called the Milstein-Platten form, which uses a numerical derivative rather than an analytic derivative. The advantage of that is it's much easier to code. Okay? So calculating the analytical form of this obviously gets more complicated the system you use, but doing a numerical derivative. The Milstein-Platten method is a numerical derivative, and it is also strongly convergent to first order, as the Milstein term is. Okay, the Euler method isn't strongly convergent, it's only weakly convergent to first order. So which is why the Milstein correction should be used. Milstein-Platten just makes it easier for me to code it up and to consider general problems. Right, the first classical aside. Okay, as I said, my background is partly in partly in quantum dynamics. I've been doing that for 25 years, before quantum computing was called quantum computing. But also, as an engineer, I also do classical filtering and classical tracking, particularly tracking of objects, okay? Tracking of objects and imagery, tracking of objects in radar. It's a bit more complicated in some respects because the things you're trying to track aren't necessarily cooperative. In fact, some of them are distinctly uncooperative because they're trying to avoid being tracked, as the Ukrainians are finding out. Right, so this is, if you like, a hierarchy of classical tracking techniques. Okay? Here we have the Kalman filter that was mentioned a couple of times last week. At the top we have optimal Bayesian estimation. This is effectively what most people are doing when they're doing SMEs, when they're doing what we call quantum filtering. They're doing Bayesian estimation. Bayesian estimation based on what they consider to be a perfect measurement record. And Peter's looking confused. Okay. So the reason for showing this slide is because there is a hierarchy of these systems in classical filtering that currently we're not using in the quantum world. Okay? All of them from here down are all approximations to this. Okay? The random finite sets here is an interesting one because it's actually some very sophisticated mathematics. There are two types of this, PhD filter by Ron Mahler and the intensity filter that's largely due to Roy Straight. I've put them on opposite sides of the list here because, as with all systems where you have a very small difference between their belief systems, there is lots of arguments and issues between the two of them. So much so that I've been to conferences where they organise parallel sessions so that the two will never meet. But they basically use different approximations for the same thing. The difference between Bayesian estimation and these random finite set methods is that the Bayesian estimation is largely computationally intractable. Okay? As soon as you start having multiple targets and the targets can swap over and you get measurements from one target that could be another target, you get false alarms and clutter and things like that, you get spurious measurements being created, then Bayesian estimation has combinatorial explosion, okay? Combinatorial computational difficulties. Random finite set solves that by throwing away all of the identity information. All you're looking at is there something there or is there not something there? But doing it in a rigorous, depending on who you believe, okay, a rigorous mathematical way. Below that you have multiple hypothesis tracking.
Lose something? Like...
Sorry? You lose the identity information about the object. So object 1 is object 1 in the Bayesian.
Oh, yeah, okay.
Okay, so it could be object 2.
So you have these permutations.
Yeah. So it's the combinatorial thing that you lose. And actually, I've been doing some work on it recently, and it's actually very, very stable and very robust, which is also good.
Okay.
Multiple hypothesis tracking is in a perfect world would be the same as Bayesian estimation, but the different hypotheses that you're propagating through the system need to be truncated. To allow you to do the computations. Below that, you have a family of techniques which can sort of be lumped into sort of, basically they're sort of, each one will have a number of possible candidate solutions which are propagated forward in time. And it's the way in which you allow those candidate solutions to interact with each other and update the probabilities that differentiates between those things. Okay? There are variants of the Kalman filter. Extended Kalman filter that some of you may have come across. Extended Kalman filters is a piecewise linearization of the standard Kalman filter for a nonlinear system. Okay? So this is the minimum thing that you can add to a Kalman filter to allow it to deal with a nonlinear system. And then something that I think has been neglected is these things called steady state filters. In many cases with a Kalman filters are very simple in the sense that they're just matrix multiplication. But when you've got matrices that are in one case I know that one of my friends wrote a Kalman filter that had 187 states, so 187 by 187 matrices, multiplied together, preferably at about 400 hertz. Okay, it starts to get computationally quite difficult. If you're only interested in the long-time behavior of your system, you're actually better off having a constant coefficient in your filter and actually using a steady state filter, what in tracking world are called alpha, beta, gamma filters. Okay? So that's, if you like, the classical world of state estimation and tracking that the engineers do. The important thing to realize about this is that there is a discontinuity. Okay? 99%, 99.9% approximately of all filters that are used live below that line. 99.9% of all papers that regard that are related to classical tracking live above the line. Okay? You don't get a publication on a common filter anymore, okay? If only. Okay? And this is the problem. There is a huge discontinuity. If all you do is read the literature of classical tracking, you start to see these things. Okay? None of them are actually used in practice in real life, apart from very, very specific applications. The same is true in control theory. Okay? When I was in Nottingham at one of Slava Belavkin's meetings a few years ago, I was talking to Ramon van Handel about optimal control theory. And we were talking for probably about sort of 3 or 4 hours. And then after about 3 hours, sort of Ramon sort of lost his temper and he said, but everybody uses optimal control theory. And I said, no, they don't. He said, but they do. I've read the papers. I said, yes, you've read the papers, but you haven't talked to the people that actually use control theory. There is a big difference between what's published and what's actually used. Okay? Even where optimal control theory is actually used in practical situations, it tends to be with constant coefficients or a lookup table, okay? Because it is impractical to do the calculations in real time. Okay? And that's the point I want to get across today. Okay. There's also a load of other processing that goes around this. So the pure computational complexity of these things, okay, is not all that's there. You need things like track clustering, track deletion, track management, and things like that. There are always errors in your system, and without some sort of intelligent processing around it, your filter can become very, very wrong. This is one of the reasons why extended Kalman filters tend to be only used in very specific applications. Extended Kalman filters are very, very good if they work well, but they're very, very bad when they work badly. Okay? Extended Kalman filters suffer from a lot of problems of nonlinear systems, of things like entrainment. They get locked into the wrong solution. And as soon as they get locked into the wrong solution, they will start to become overconfident that that solution is the right one. Okay? And they can be distracted, if you like. So there's lots of other processing that goes around any classical tracking system. Right. So come back to the first application I want to talk about, which is the Hamiltonian or frequency estimation. This was work that I did with Kurt Jacobs and Charles Hill a few years ago. We have a single qubit. The Hamiltonian generates rotation is about the block x-axis, and the measurement is along the block z-axis. So we have an SME that looks like this, and we have a measurement signal that looks like this. Okay? It's interesting because it's something like a charge qubit. Okay? Right. Now the problem is that if you have an error in your omega, here, your qubit frequency, then if you're trying to estimate your state, then the state will include the state that you're estimating. Okay, your best guess of what the quantity of the qubit is doing will include errors, and as the error in that frequency increases, you find that the fidelity of your estimated state decreases quite rapidly. So with a 1% error, you get about 99%, a 2% error, 97%, and then down to about 80% with a 5% error. Okay? So that determines roughly how much accuracy you need in your qubit frequency.
Is this a dynamical? I mean, this error changes, or is it like a fixed?
It fluctuates. Well, the error in the state estimate fluctuates, but on average, it looks like this. It saturates to a level. Okay.
Excuse me. Are you doing QND measurement?
No, sorry, continuous weak measurement.
Ah.
Okay, so this is quantum filtering. Okay, all right. So if you look at and it's a function of things like the measurement strength and the measurement strength and the percentage error. Okay, so you've got graphs like this. So basically, the stronger you measure, the less important these errors are. The weaker you measure, then obviously the more important they are. Crucially, though, the stronger you measure, the more influence you have on the evolution of the system. So the more you suppress the natural qubit, the evolution of the qubit. Okay? And if you plot the 1 over the average fidelity, so the average infidelity, which is a term I hate, the average infidelity for different coupling values, then you get graphs like this. Okay? So if I wanted to say, if I wanted to have an average infidelity of a certain level, say 1%, then I can then determine what my fractional error in frequency should be for a given measurement strength. Okay? So this is the, if I want to get to this point here, then, or this point here, then what I need to do is have a fractional error of that for a very strong measurement, and for a weak measurement it would be down here somewhere. Okay? So the more, so the further down you want to get here, the more demanding the fractional error requirement is. Okay? The obvious thing to do as a physicist is to use the best technique possible, okay? Bayesian inference. Okay? You can set up the SME, or a hybrid master equation as Kurt calls it, with the parameter, be it the qubit state, the qubit frequency as a parameter within that SME, and run parallel SMEs and have an update equation which has a classical probability for the parameter, for the classical Hamiltonian parameter, and have the normal stochastic master equation for each of those values. Okay? So you have all of this, and what you get is as a function of time, you can indeed estimate the frequency. Okay? And if you look at the saturation level, or the asymptotic accuracy error as a function of measurement strength, you get a graph something like this. Okay? So your best guess of the frequency error using this sort of optimal Bayesian technique is this. Okay? But going back to what I said about the optimal Bayesian technique,
it seems like it's going back up. Is there an artifact?
That's partly to do with the. I think that's partly to do with the back action of the qubit, because obviously the stronger the measurement, we looked at that in detail, and that is a real effect, and we couldn't go much beyond that, unfortunately, because of the computational complexity of the system. But definitely that seems to be where the back action is having a significant effect on that evolution. So it then becomes harder to characterize. It's partly that if you think about it as a single peak in a very large sea of noise, that peak starts to broaden. So then it becomes more difficult to estimate where that is.
What is the definition of measurement strength?
The measurement strength is in the equation. So it's basically it's the rate at which it's a rate that they use in quantum optics. So it's, if I find it. There you go. So it's that value there. Okay.
Sort of coupling.
It's a coupling constant, yeah, coupling constant between your measurement and your.
It's square root of the coupling constant, isn't it? Because it goes like square root of dt.
I know that. Yeah, I know Kurt and I, when we were doing this, we had a problem because I was using kappa there and kappa squared, and Kurt said that that's important from a quantum optics point of view because that's some rate that occurs in quantum optics, which is.
So basically, the coupling is square root of dt times square root of k.
Yeah.
Yeah.
Are there any other decoherence processes other than measurement?
In this case, no. Okay. I mean, in principle, that you could add in other things, but obviously.
In every instance.
I'm a theorist, so I can just cross those out.
Okay.
Being a theorist is wonderful.
Well, you were trying to be practical.
Theoretical engineering. I'm a practical theorist. Okay. So the point is there's a finite limit to what this asymptotic frequency error is for any system. Okay. But the thing is, this particular problem, estimating a harmonic frequency, a harmonic signal within a very large sea of noise, is a well-known classical problem. It's a problem that occurs in things like radios, things like radar, and things like that. There are three basic techniques that people use to do this. One is the old-fashioned Fourier-based methods. Okay. Fourier-based methods, obviously, they can transfer everything to the frequency domain. You have a nice sea of noise, and you have a peak. You try and identify the peak. Notch filters are an interesting one. What a notch filter does is, if you think about it, it operates in the time domain, but if you think about it as a very large sea of noise in the frequency domain and a single peak, what the notch filter does is it will move a filter to cancel out that particular peak. Okay? And that's what the notch filter does. And the advantage of that technique is it doesn't require a Fourier transform. It can be applied purely in the time domain. The other type of technique, the one that I'm going to talk about is called music, but it's called a noise subspace technique, which uses the correlations within the signal to isolate the subspaces which contain that harmonic term. They're very different techniques, and we tried one from each of those techniques. So we tried the periodogram, Quinn-Fernandez, which is a notch filter, and music, which is a subspace technique. In the long time limit, they should be, if it's a classical signal, classical harmonic signal in noise, then they should reach the Kramer-Rao band. So they should give you optimal performance. Now, the slight complexity with that is the fact that they won't actually reach the Kramer-Rao band in many cases because of the broadening of that peak, because it's no longer a single frequency. Okay, so it's no longer a single harmonic. The problem is complicated by the fact by two factors. One is the fact that it's very, very low signal-to-noise ratio. If you calculate the classical signal-to-noise ratio in the measurement signal, it turns out to be about -30 to -20 dB. These classical techniques typically will fall apart at about -20 dB. Okay, so this is exactly the range of parameters within the system, or noise within the system, where these classical techniques would be expected to fail. But we thought we'd try them anyway. And the final one was the back action that I already mentioned. It will broaden the peak. So actually, if you couple too strongly, you'll broaden that peak sufficiently that you can't find it because it's no longer a simple sinusoid.
So if there are no other noise processes, what prevents you from just integrating for forever?
Okay, you're an experimentalist.
Yeah.
Okay, how long can you integrate?
You just keep collecting.
Yeah, I mean, there's numerical artifacts and things. There's a limit to how long you can integrate. I mean, if you wanted to do it online, that's the ultimate aim of this. Okay.
Well, but if there's no time, there's no penalty due waiting because there's no other noise processes. Why is that to be done online?
I don't know. My experience is experimentalists don't like waiting around for days to characterize the qubits or characterize the experimental system, unless you have very, very accommodating grad students. I also, from a practical level, I also have a limitation in terms of how long I can wait for the simulation. So I'm trying to do it efficiently, and I'm trying to do it as well as I can. Okay. Right, the periodogram. Periodogram is a continuous function of frequency, and all you're trying to do is you're trying to maximize that value. Okay. If anyone has a go at this, be very careful in MATLAB about using the periodogram function in MATLAB. And the reason I say that is I had finally a project student who was doing this, and all he did was looked at the MATLAB. MATLAB had a periodogram function, so he used it. And what he found was that the periodogram function in MATLAB gave identical results to the discrete Fourier transform. The reason being that the periodogram function in MATLAB is the discrete Fourier transform. It's not actually a periodogram. So be careful. Any built-in functions, try not to use them, because this is a continuous function of frequency. Okay? So there are differences. This is better than just using the discrete Fourier transform. Quinn-Fernandez method, as I said, is a notch filter. It uses cancellation of the signal. So effectively what you're trying to do is you're trying to reduce the noise, the noise signal to basically a flat, or whatever bandwidth band you're using, a flat thing with a notch in it. Okay? If the peak is still there, then you move the notch using an adaptive filter equation. So basically it's quite complicated, but it does work. The technique is there if you're interested. And it does work, and it does work well. Okay? The problem being that at these particular noise levels, you get multiple solutions. So if the noise was half as much as it was, or h bar was a little bit smaller, then you would only get a single solution, and it would work fine. The problem here is that actually you get multiple possible solutions depending on where you initialize your filter. Okay? So there's a problem there. Final one is music or multiple signal characterization. Starts by constructing this symmetric matrix, autocovariances between the different signals given by that, and you do some subspace transformations. Obviously, there are papers, and these are all mentioned in the paper that we wrote, and I'm running out of time, so this is probably a more sophisticated technique, a bit more computationally expensive. The advantage is that you get a single output. The disadvantage, so you get a single output for your frequency rather than multiple outputs that you get for your Quinn-Fernandez. The disadvantage is you need to know how many frequencies you're looking for. Okay? So there are pros and cons with all of these techniques. So And that's the output of the music technique. Okay, that's called the music spectrum, and you're just trying to detect that peak there. And if you do that as a function of time, it gradually settles down to the right value. Okay. All right. So this was done about 3 years ago, and the results for the Bayesian method were about. It's all tried to keep it as close as possible. So 500 cycles, 5,000 realization per K value, 4,000 steps, blah, blah, blah. Approximately 33 hours per K value. In this case, classical methods, in this case they used 232 processors. It also took just over 30 hours per K value, the difference being they used a single desktop computer, non-optimized. And these are the sorts of results that we got. The frequency error for the Bayesian technique is down here. The purple one is music. The red crosses are the periodogram. And the green lines, this is the actual Quinn-Fernandez performance. This is how good Quinn-Fernandez would be if you had a very accurate estimate to start with. Because the closer, because of this problem with the multiple solutions, the closer you are to the real value, then the closer you are to the real value, then the closer your estimate will be. Because obviously if your estimate starts off up here, then you're more likely to get something that's way off. Okay. So that's the sort of graph that you get. So music, the music, the subspace technique, the frequency technique, and then the time domain technique. And then that's the optimal Bayesian. That's where we're aiming for. Okay. Right. As we increase the coupling value, you can see the periodogram deteriorates very rapidly. The music is okay, and you can see that the Quinn-Fernandez technique, the notch filtering technique, tends to sort of be more or less stable. And then increasing it even further, this is because this appears to be better than the Bayesian technique. In fact, it never will be, because this is just the theoretical limit of the Quinn-Fernandez technique if you have a very accurate estimate and if your signal is a pure sinusoid, which at this level it wouldn't be. But here you can see that the periodogram signal, the error in the periodogram signal is very bad now. Quinn-Fernandez is more or less stable, and the music performance is quite good. And if you plot those on the graph I had before, you can see roughly where they are. So periodogram deteriorates very rapidly with coupling strength. The Quinn-Fernandez is more or less stable, and music increases slightly, performance slightly as you increase the coupling strength. And these are the Bayesian ones down here. So music is actually fairly close, reasonably close to the Bayesian technique. So it's not a bad technique.
Yes, could you estimate how good this would work if I had, like, let's say 2 parameters to estimate?
We could do, but I haven't done it yet. There's certainly hope. I mean, with all of these things, there are classical techniques to take something which is just a pure classical signal and extract various different parameters out of it. The point I'm trying to make is that the way that we would normally approach it within physics is to use sort of everything, use the whole optimal Bayesian. But actually, for a lot of systems, that's not really necessary. Okay, so you're trying to simplify it to do this. Okay. But yes, I mean those techniques do exist. You just need to know something about the nature of the signal and what the parameters are that you're trying to estimate. So, for example, with the sinusoidal techniques, in this case, I've chosen sinusoidal signal detection, signal estimation techniques, which estimate the frequency very well. But there are other ones that estimate the phase of that signal and the amplitude of that signal. So you can do a variety of things just even with a simple sinusoid. Okay. Right, the next thing I want to talk about is reduced information measurements. Okay, this is some work I've been doing for a few years with people like Kurt Jacobs and Howard Wiseman. Okay, if you look at the quantum state itself, if you start from a completely unknown state, single qubit, sitting in the middle of the Bloch sphere, the mixed state just sits in the middle of the Bloch sphere. By generating the measurement record and interpreting that measurement using the SME, what you're doing is you're purifying the state. Okay. So purifying the state, and eventually, as you accumulate more information, it will start to lie on the block sphere. Okay? In this case, it's rotating about the x-axis. Okay? So that's what we're talking about in terms of purification. Right. Kurt Jacobs was the first one to realize that actually, if you allow yourself to do feedback in this, if you take your qubit and you rotate your qubit onto the horizontal plane, which is perpendicular to your measurement axis, then you can speed up the measurement process. The average purity will increase by a factor of 2. Oh, sorry, the average purification rate will increase by a factor of 2. Okay. I did some numerics on this and went over to visit Howard in Brisbane and pointed out that I was not getting the same results doing the numerics, and Howard went away and solved the Fokker-Planck equation. About half an hour later, we had a reason why. Actually, it's to do with the fact that if you're interested in the average rate of purification, then Kurt is technically correct. But if you're interested in the average rate to reach a given purification level, that's what's called the first passage time, then actually rotating it towards the measurement axis is twice as fast. The reason for that is that when the distribution that you generate with these rotations, if you rotate towards the measurement axis, that distribution has an extremely long tail, okay? And that very, very long tail has a disproportionate effect on the average rate of purification. But if you want 99.9% of your qubits to purify very quickly, you're better off rotating towards the measurement axis rather than away from the measurement axis.
But if I set like purity 1, what is the? I'm not getting this. So say I use the second.
Well, you start with a
say,
completely unmixed state, so it says purity of a half.
Yes.
Okay, so gradually the purity will increase.
Yes.
It will gradually reach the thing, and in the long time limit, it will reach purity of 1.
Yeah.
The length of time it takes to reach that
Yes.
purity, or 99.9999999, is quicker if you, on average, if you do that. But the average purification, because there are a few qubits when you do that, they just won't purify at all. And that has a disproportionate effect on the average purification rate, because the distribution is extremely skewed towards that tail. So in 0.0001% of cases, it just won't purify at all. So when you average all of those, you find that the average rate of purification for this is longer.
Okay, I get.
If you have dephasing, probably the second method will still be better.
Certainly, it seems to be more robust. The benefit that you get, we did we wrote a paper and we did some numerics on practical applications of this. And actually, what you find is that it's if you like, the last third of the purification that actually where most of the information is, where most of the benefit occurs. In the case of this one, measurement axis, it's basically, you only need to be within a small angle, a relatively broad angular range of the measurement axis, whereas with Kurt's one, it's much more sensitive to being very close to that horizontal plane. I've also done some other stuff that I talked about in Nottingham, where I looked at high-pass filters for this, and actually what you find is that Kurt's method deteriorates quite rapidly once you filter that high-frequency noise. And the reason for that, I think, is that because Kurt's is deterministic, he rotates to the measurement axis, so it actually effectively nulls out the stochastics. So it's purely deterministic. Then, effectively, you have to follow all of those small stochastic changes to keep it there. And if you have a low-pass filter which filters out all of the high-frequency components, it's more difficult to do. Whereas this method here, the one that Howard and I looked at, it is much more robust to those sorts of errors. Okay, but have a look at the measurement record for a second. Okay, I'll try and speed up a little bit. I'm particularly interested here in the bit there. Okay, the reason for that is an effect from classical stochastics. There's a thing called stochastic resonance, there are two types of stochastic resonance. There's what's called subthreshold stochastic resonance, where things flop between two bistable wells. This one is the one that I'm interested in here, called suprathreshold stochastic resonance. And what it shows is that basically the number of, you can increase the amount of information transferred through a channel by reducing the number of bits that you're passing. Or you don't need the number of bits to maximize the information. Okay. In particular, if you look at the optimal distribution of quantization levels within your signal, classical quantization or discretization levels within your signal, which this is the optimum condition for a Gaussian system. That's called Lloyd max quantization. Classical quantization, discretization, not quantum quantization. It's very complicated. If you look at where those optimum quantization thresholds are, you find that for the low noise case, those optimum discretization levels, quantization levels, are more or less Gaussian distributed, okay, which is intuitively correct. What you find as you increase the noise, okay, moving from here to there, in this case, Nigel, who wrote this paper, plotted this as noise to signal ratio rather than signal to noise ratio, which really stresses me out. There you go. What they found was that actually as you increase the noise, you find that some of these quantization levels, these optimal quantization levels, actually start to collapse into single levels, to the point here where actually your optimum number of quantization levels is in fact 1. So only having a single bit is the best thing that you can do. Now, in the signals that we're dealing with in the quantum filtering, it's very, very high noise. So actually, the first thing to do is say, well, okay, why don't we try it out with 1 bit? So that's what we did. We truncated the measurement record to a single bit. So the measurement record now looks like this, and just plugged that measurement record into the quantum filter to see what happened. Okay? The rationalization for that was the fact that this is actually, in classical systems, this works well, but this works well. The question here is, can you get all of the information that you require out of the quantum system just by having a single bit for each measurement signal? And in fact, you'd be surprised, but may not be surprised, but yes, the answer is yes. I wouldn't be talking about it if you didn't. So same example again, single qubit with a Z measurement and X rotation. And one qubit with no feedback. Okay. This is the average fidelity. Okay. This is the optimum fidelity. This is the fidelity with one qubit of measurement, with 1 bit of measurement signal. This is the full measurement record. And this is a simple example. It's the average fidelity, and that's a single example of the fidelity. So what you find is that it reaches a purity of 1 and then sort of will drop, okay, as these errors increase. With feedback control, using the rotation towards the measurement axis, you find that actually the average fidelity does asymptote to 1. So in fact, it doesn't converge quite as fast as you might expect, but actually you can reach a very high purity state just by using a single bit per measurement sample. Okay? And it's relatively insensitive to the angular error of your rotation. So here it's sort of within about 10, 15 degrees, you'll find. So it's also very robust as well as being practical. Okay. The interesting question is, well, that's a single qubit. Can you do the same thing for 2 qubits? And in fact, you can. In this case, we looked at a number of different systems. This is the one that seems to work better. It's a ZZ interaction generating an entangled state, and it's combined with 2 local Z measurements, and in this case, no control. What we find is that the fidelity for the 2 qubit system also asymptotes to 1, so we're confident that it generates a good quantum state estimate just using that 1 bit per measurement. And then looking at the classical and quantum correlations, you can see that it also reproduces, the estimated state also reproduces fairly or very faithfully both the classical correlations, which are the red lines, and the quantum correlations measured by the discord on the blue lines. Okay? This is the full measurement record, and this is the 1 bit record, and again, this is the full measurement record and the 1 bit record. As you might expect, certainly as I was expecting. The classical correlations are easier to measure than the quantum correlations, but the quantum correlations can still be measured just using a single bit per time step. Okay, so just about in time. So just to summarize, what I'm interested in is efficient quantum filtering, where the quantum filter can be truncated or approximated to allow more practical calculations than the full Bayesian techniques to be implemented. It is not that you're going to find new physics there, but it will potentially would allow you to do more interesting, or potentially allow you to do more practical control experiments by using reduced quantum filters that are fit for purpose. Okay, this goes back to the point I made about the classical tracking techniques. Is that the paper practicality discontinuity? Okay, when we're publishing papers, we want to be well above that line. When we're actually building things, we want to be below that line. Okay, and that's the thing. I think in the quantum filtering world, people are looking at very simple filters and they're looking at very complicated filters, but there's not that range of techniques that we've developed yet, because these techniques have developed over the last 30 or 40 years, okay, in the classical system. So I used a couple of classical techniques to do things like parameter estimation for qubit frequencies, and I've talked about the signals, the measurement signals that could be used in incoherent feedback control. And they have to be treated as classical signals. You have to worry about things like the bit depth. You have to worry about the bandwidth. I haven't had time to talk about that, but I've done some work on that. Things like dynamic range. Okay, what's the dynamic range of your system? At what point does the measurement saturate? Okay? And also things like the sampling frequency, obviously related to bandwidth, but it's slightly different. Right, so very lastly, what I want to say is that there are a couple of outstanding issues that I think are important for this. One is I'll start with number 2. One is the numerical stability of the filters, and this is something I'm talking to Pierre about at the moment. The standard Milstein techniques are fairly sensitive and fairly unstable. Pierre's seems to be much more stable. I'll be looking at that over the next week or so. I'm particularly interested in reducing the computational complexity of the system to try to implement these things in real time. Modern FPGAs are approaching the frequencies that would be required for real-time feedback, state estimation and feedback control for things like solid-state qubits. Yeah, there have already been a couple of experiments on sort of, if you like, the sort of direct feedback, so measurement record feedback, but no one, as far as I know, has actually managed to do quantum state estimation feedback within a quantum system. Process noise for quantum filters is an interesting one. In classical filters, process noise plays the role of a tuning parameter. Okay? Process noise within a Kalman filter represents all of the errors in your system, both in terms of nonlinearities and in terms of characterization of the physical dynamical parameters within the system. And to date, this really hasn't been addressed very fully in the quantum filter world. Finally, this one I think is probably the most important thing, the coupling strength. This was pointed out to me by Daniel Lloyd from Strathclyde, because I was interested in errors in the coupling strength. And I mentioned this to him, and he suddenly goes, well, coupling strength doesn't matter. I said, what do you mean? He said, well, it's insensitive to it. If you run the quantum filter equations, and went away and did it, and what I found was that the coupling strength in the quantum filter equation, you can have errors of between about 10 and 20% within the equation, and you still get purify the state fine. Okay? It is not completely insensitive, but it is very insensitive to the value of that coupling parameter. Now, instinctively, that seems wrong, because for 2 reasons. One is my physical intuition says that actually the degree to which I couple into a system, particularly a quantum system, should be important. Okay? The second reason is, if it is so insensitive to that value, how do you measure it? It needs to be sensitive. If you're trying to measure something, you need to exploit a sensitivity in the system. Because if you try and measure something and you get something within 10 or 20% and you can't do better than that, then there's a problem there. So measuring that value is part of what you want to do within a quantum filter. Now, I think I've got some ideas about why that might be the case. And that's one of the things that I'm interested in talking to people about. Okay. But thank you. That's fine.
completely
I might not
ridiculous.
either.
I think it's a good reason to ask the question. So you mentioned that some of these techniques will not reach the Kramer-Rao bound
Yeah.
because of the broadening, which is due to that action.
Yeah,
More or
because
less.
that's the Kramer-Rao bound defined for single
But that is a
harmonic.
classical Kramer-Rao bound.
Yeah,
And you use the quantum one as a benchmark?
I could do, but I haven't done it yet.
Okay.
The whole thing about being head of
But that
department.
should take into account
Yeah,
back
yeah.
action. And
Well, that's the thing. I mean, Kurt's Bayesian technique that took 232 processors a day and a half to calculate, that will take it into account. So that was what we were using as the benchmark. As long as we could explain why that particular curve fell below that, then I was happy, because that particular curve was unattainable anyway.
Okay, yeah, sure.
So
Which quantum camera?
I don't know, quantum Fisher information went over that. That's what I mentioned. I don't know.
there's
what
probably a
about
whole
quantum.
discussion about which one to
Yeah.
use.
Even the classical camera one, this is a classical process with correlation, so you need to compute this asymptotic Fisher information for the output process.
And that's been done. It's been done, and it's for a single sinusoid in white noise. That's been done, and it's in the. We didn't do it, but it's quoted in the paper. Yeah.
Particular model.
But why is it not well defined? I don't know exactly. As I mentioned, what's the problem in the?
So
Say you have this process and there's this parameter. And
so maybe you can compute it on some particular models, but in general, this is a process that is non-Markovian. Yeah, it's the measurement process, and the Fisher information is only, you can write it as a limit of Fisher informations for time t, but there is no closed form expression for it.
Okay, so it's not computable in general.
Typically in the classical signal processing world, what they tend to do is that the meeting with Kramer-Rao bound is that they look at the order of convergence, and that's what they're really interested in. I think that from memory, the order of convergence for Kramer-Rao bound was t to the minus 3. And what they do is that they then show that some of those techniques, like the Quinn-Fernandez, there's a theoretical thing that I've gone through that actually shows that the convergence is t to the minus 3. So that's what they would say is meets the Kramer-Rao bound. The coefficient is irrelevant from that point of view. It's the asymptotic behavior.
In the case of two qubits, do you think you can create entanglement by using feedback control?
We certainly should, well, with the reduced bit measurement.
Yeah.
With the reduced bit measurement and feedback control, what we've shown is you don't completely destroy it. So you need some other process to generate it. The problem is that when we looked at this, I looked at a number of different systems where you have either measurement-induced entanglement or sort of interaction-induced entanglement. And what we found was that basically that was the one that seemed to work best. The problem is that the more measurements.
Yes.
The answer is a qualified yes. You don't destroy entanglement which is created by another source. Okay, but I wouldn't say for definite yes you can create entanglement with a 1-bit record, but you don't destroy entanglement. If the entanglement is created by an interaction, you don't destroy it by applying feedback. Okay, so it's qualified, yeah.
So when you do this 1-bit record, this depends on the frequency of sampling.
Yeah, effectively you're doing an implicit time averaging.
Yeah.
The other stuff that I've done that I talked about in Nottingham was looking at what's the minimum number of bits that you need to purify a system.
Right. So
And that's, I know, Andrew, Andrew, I mentioned this at Nottingham, but I presented that particular work at the APS in Boston, and Andrew was the chair of that session. And there was a throwaway comment about the 40 kilobytes. And the minimum that I could get away with to purify a single qubit and have a stable filter was about 40 kilobytes. And Andrew asked me about that afterwards. But that seems to be about the ballpark figure, is that if your sampling rate is too slow, or your bit depth is too small, or your bandwidth is too small, then the filter becomes unstable. It only becomes stable and purifies nicely over a period of time when the the total amount of information you extract is about 40 kilobytes.
Is there a sharp transition between this regime, or?
No, we've done some more work on this. Neil Oxtoby did some calculations on this that we didn't have time to do before we presented at Nottingham a while ago. And basically, it's not a hard transition because it's then a case of, well, to what extent do you say is it stable or unstable? Is it 99% stable and 1% unstable and things? So, but it's about 40 kilobytes. Seems to be about the things. Now, what I've done is I've done bandwidth, sampling rate, bit depth, quantization of the shifting the quantization levels using the Lloyd Max quantization. So having things like a compander, compressor, expander for the discrete levels and things. I've tried everything I can think of, and it always comes down to about 40 kilobytes.
And the dependence on the parameters like omega and coupling strengths?
Again, certainly for fairly weak measurement strengths, if you double the measurement strength, it takes half the time. So yeah, it's more or less proportional. As you start to have stronger and stronger measurement strengths, then obviously you're interfering with the natural evolution of the system, and then it goes a little bit different. The way I think it was Josh Coombs pointed this out. He said, well, actually, what you're doing is not just measuring the qubit. You're actually measuring and validating that oscillation, all the parameters that you're using as well. So that's where the 40 kilobytes comes from. But I've also done some stuff. We're looking at how many bits. What's the minimum number of bits you need for 2 qubits, entangled qubits, and it seems to be it's still roughly 40 kilobytes. So it's not, 40 kilobytes per qubit. So it's something that I haven't had a chance to go back to sort of do systematically, because the problem that I've got is that it's defining what you count as being stable or unstable or good enough purification, because it's a fuzzy sort of target that you're aiming at. Maybe we can talk about that.
Have you investigated these in presence of a thermalization?
No, not yet. No. I mean, obviously, that's a factor as well. I mean, the sort of solid-state qubits that I would normally be interested in, normally you'd assume that the frequency is sufficiently high that thermal effects are fairly small.
The dephasing you have already considered.
Yeah, I mean, you can chuck in as many different environments as you like, and that's one of the reasons I'm interested in Pierre's different numerical scheme, because the beauty of that is it makes the numerical filtering much more stable, and there are ways to introduce all of these additional terms. Yeah, nearly finished on time as well.
Very good time.